we discussed about the waveform. So we call this is control. This is fundamental. We call this is carrier. This is triangular carrier. So first we compare the frequency. The triangular frequency should be higher than the control frequency, right? And we have index. So the index is MF to compare the frequency ratio. So MF is equal to Fs divided by F1. So this is carrier frequency. This is sine wave frequency. Sinusoidal wave frequency or fundamental frequency. So internal carrier is 10 kilohertz. Fundamental is 60 hertz. So how many times? 166, right? If half wave, then 83 times. What does this mean? Means if you have half cycle, how many carrier in here? 83, right? 83. So we have how many switching times? 83 times. So do you think it is better or it is worse than square wave? For square wave, we have this waveform. But now, for carrier, we have this waveform. So which one is close to sinusoidal? Square wave or pita band? Which one is better? Pita band, right? Because you can see the resolution improved. They switch a lot. So if I walk 1, 2, 3, 4, then I can not reach this point. But if I walk this way, then I can reach any point. So if you need high resolution, your pulse width should be narrowed down, right? So we create more opportunity like this. We can create the duty maybe 0.9. The duty here maybe 0.95, and here only 0.1. So we can change the duty cycle a lot. Then it is better. So this is the MF. So MF, we should push MF as larger as possible. However, if you push too large, then you have physical limitation because your switching loss is too huge. Then your power device burn out. So do you like to burn out your power device? No. So you still have limitation, maybe 10 kilohertz. How about another index we call MA? What is MA? It is the amplitude of the control divided by the amplitude of triangular. So we compare the amplitude. So here, what is your triangular amplitude here? So it could be 1 volt minus 1 volt. How about the amplitude of sinusoid? 0.9, right? So if I push the sinusoidal waveform to very large amplitude, huge amplitude, then what happens? So I have a carrier, it is 1 volt, plus and minus 1 volt. So like this, and it is 10 kilohertz. So it is 10 kilohertz, and it is plus minus 1 volt. Now I push the sinusoidal waveform like this. Then what happens? I put my sinusoidal waveform to very huge compared to the sinusoidal waveform. Then what happens? So we follow the rule. If the sinusoid is larger than triangular, then T1 is turned off, right? And then we can create 0.5 VDC. So in this one, the sinusoid is larger than triangular. Then what happens? T1 turn on, right? If T1 turn on, then we can get 0.5 volt, 0.5 VDC, because T1 is turned on. T1 is on. After that, you can see triangular always larger than sinusoid, right? So sinusoid is less than triangular. Then we can get T1 prime on. So in here, we can T1 prime on. T1 prime on, then need minus 0.5 dBc. So here. And then after here, we repeat. So it becomes on and then off. So what kind of switching can we get? Anybody has any idea? If we push sinusoid very huge, then what happens? Square wave. We go back to original, right? So what is this way? 6-step square wave. So this is 6-step square wave. So do you like this? No. You like PWM? But no, PWM doesn't work. Why PWM doesn't work? Because your sinusoid is too huge. So do you need to limit your sinusoid? Yes. So what is the maximum value for your sinusoid? 1. So my peak value of sinusoid will be here. Then it is okay, right? Then I can get PWM. So we have a limitation for what? MA. MA. So what is MA? The sinusoid amplitude divided by the triangular amplitude. Sinusoid amplitude divided by the triangular amplitude. So sinusoid amplitude should be equal or less than triangular. So it should be equal or less than what? 1.0, right? So 1.0 is the maximum. You cannot over. If you over, then this one do not have PWM. It is useless. So we can see the maximum point cannot over 1.0. So we call this is MA. So you have to follow this rule. If you do this, we call this is over modulation. We call this is over modulation. Like an operation amplifier. You have operation amplifier. This is 10 kilohertz. This is 1 kilohertz minus plus. If this is 1 volt, how about this voltage? Minus 10 volt. If this is 0.5 volt, how about this? Minus 5 volt. If this is 10 volt, then what happens? Can you say, here I can get minus 100 volt? No, because it will saturation. So maximize minus 15 volt, right? You saturate. So if you have amplifier, you cannot saturate your amplifier. Otherwise, you will create a linear distortion. If you design PWM, you cannot saturate your PWM. So your sine wave cannot be oval than triangular. Otherwise, you become over modulation. If you over modulation, then you become nonlinear. So we have some limitation. So you have to follow the rule. Otherwise, your PWM just doesn't work. Okay? So we know the idea. So now we can use triangular. We can use sine wave we can design operation amplifier to compare. So then we can determine T1 on or T1 from on. So what is your output voltage? Your output voltage is equal to V control divided by V triangular. So if this one is larger, then output is larger. If this one become half, sine wave become half, output should be half, right? So your output is proportional to MA. So this is MA. However, if this is 1 volt, this is 1 volt, your output is not 1 volt. Your output is maybe 100 volt, right? So you have to multiply by another vector, VDC divided by 2, right? Because here, only on and off. On is 0.5 VDC, off is minus 0.5 VDC. But VDC could be 200 volt. So this becomes 100 volt minus 100 volt, right? So you have to use this rule. So this is the amplitude of the sinusoid. So this is the amplitude of each phase. Okay, so we know this is the result. This is the result. So how about fundamental? This is amplitude. How about fundamental? So fundamental is equal to VDC divided by 2. But fundamental, sometimes I do not put this as 1, maybe half. So if the amplitude becomes less, then the output becomes less, right? So the output should be proportional to what? To MA. So if the MA becomes larger, output becomes larger. If MA becomes smaller, output becomes smaller. If MA equal to 1, then we can get maximum output. So the fundamental should be multiplied by sine omega t. So the output of fundamental is like this. So this is the amplitude. So this is V A or 1. This is the amplitude. And the waveform is sinusoid, right? And how about frequency? Maybe 60 Hertz multiplied by 2 pi f. So we can get the waveform like this. So this is the main idea. So we can get, if we put the sinusoid become higher, then output become higher. But the sinusoid cannot over triangular, right? So if the ratio is 1.0, then I can get maximum output. If the ratio is half, then output is half. So we also can control the frequency because we can change the frequency of the sinusoid. Then we can change the frequency of output. So the idea is very clear. So you know your fundamental. So what is your fundamental? Your fundamental is here. What is your frequency? Maybe omega 1 or f1. So it is 60 Hertz. So the peak value will be 1.0. Okay. So this is your fundamental. So my question is, then what is your harmonics? Do you have 5th harmonics? Do you have 7th harmonics? Do you have 11th harmonics? Do you have 13th harmonics? So how about your harmonics? So then you have to use Fourier series to analyze this waveform. After you use Fourier series, you can prove no 5th, no 7th, no 11th, no 13th, no 17th, no 19th. So where is your harmonics? Your harmonics go to your carrier, 10 kHz. Near 10 kHz, you found your harmonics. So you push your harmonics to high frequency. So what is the amplitude? It could be 0.8. And you have side harmonics near 10 kilohertz. You have small harmonics. How about the next one? 20 kilohertz. Maybe 0.4. And you also have side band. And how about the next one? 30 kilohertz. So it is related to the carrier. So do you think this is a good thing or this is bad thing? You push your harmonics to carrier. Is it good or is it bad? Before you have 5 harmonics here, 7 harmonics here, right? 11 harmonics here, 13 harmonics here. And then you cannot design filter because it is too close, right? But now, the harmonics are far away. So do you think this is a good thing or this is a bad thing? So you have a voltage. And you have inductance. You have resistance. And you have back EMF. Because you put the voltage into motor. So back EMF, if you think, I don't know, so I neglect back EMF. Resistance, quite small, so I neglect resistance. I only consider inductance, right? So what is the current harmonics? This is voltage harmonics. Then voltage harmonics go to inductance, resistance, back EMF. So how about my current harmonics? It is equal to voltage harmonics divided by impedance, right? Impedance. If this one, then how about the carrier frequency? It is this one divided by this, so 166 times. So the frequency becomes 166 times. So this is VTH. And we consider inductance, right? Inductance. But the frequency is not 60 Hertz. The frequency becomes what? 10 kilohertz. So it is 166 multiplied by L. So the same L as fundamental. This one becomes 0.8. But this one increased to 200 times. Then how about your current? Your current becomes very small because 0.8 divided by 20 times becomes 0.004. A liter, right? A liter. So what is the advantage of high frequency? Because during high frequency, your inductance reactance become large. If your inductance reactance become large, then your inductance current become very small. If your inductance current is small, then your harmonics current is small. If your harmonics current is small, your loss is small. Your ripple is small. So before, if you use the 6th step, what is your current? It will be like this. Because you have a lot of harmonics. After you use this, what is your current? Your current becomes this. We saw the video, right? Like this. So which one is better? Do you like this one or do you like this one? This one. So you can see the advantage. You push the switching frequency to higher, then your current harmonics become smaller. If your current harmonics become smaller, your waveform is more close to fundamental, and your loss become smaller. Then it is a good thing. So people found, oh, this is good. This is better than 6th step. So it is easy to implement. However, you still have some rule. What is your rule? you cannot put sinusoidal amplitude too large because you have to do linear regulation. So this is 1.0. This is we call MA. So MA is equal to VA0 and 0.5 VDC. Or MA is equal to V control divided by V carrier or V triangular. So your control cannot become too large. You cannot over triangular. So the maxima should be 1.0. So here is linear. If you increase your MA, then increase your output, right? But after that, it becomes square wave, right? So it is like this. Saturate. So if you increase your sinusoid to 100 times, I increase to 100 times. Can I get 100 times output voltage? No. The maximum is 1.2. This is 1.278. This is saturate. So this is linear. So we call this is over modulation. We call this is linear modulation. So if you design PWM modulation, you have to be very careful. Your sinusoid waveform cannot over triangular. Otherwise, you get a lot of trouble, right? Your modulator become useless. Okay. So this is fundamental idea. So now I ask you one question. How can you implement your circuit, the sinusoidal waveform circuit? You can say, oh, it is easy. I can design operation amplifier. So I can create 60 Hz here. And I can use triangular generator. This is OPA. I can generate triangular, right? And I can compare. Then I can determine T1 is 1 or T1 is 0. Then I can design the PWM easily. Maybe only 3 or 4 operation amplifier. It is cheap. And the performance is good. And another student think, can I generate the triangular by using a DSP? We have timer, right? Timer, we can count up. And when reach the maximum value, and down, up, down. Can we use a timer to generate triangular? Okay, no problem. Can we use program to generate sinusoidal waveform? Okay, so we can compare our sinusoidal waveform and triangular by using DSP. Then we can generate 1 or 0. So you also can use software. You can use hardware like this. You also can use software. Both are okay. So you can use different way to implement the idea. So it is easy, not too hard. So people feel satisfied about this technique and use for a long time. However, if you use this technique to your drive system, then you have to ask, what is the performance? If you use 6-step square waveform, then what is the maximum speed? 1,800 RPM. What is your minimum speed? Your minimum speed could be 120 RPM. So what is your adjusted speed ratio? 1/5 divided by 1, right? 50 times. So this is adjustable ratio. If you change to sinusoidal modulation, Then what is your maximum speed? The same. What is your minimum speed? 30 RPM. So what is the improvement? 60 to 1. So which one is better? This one, right? It is better. But now you have a question. How about if I need 1 RPM? I don't satisfy with 30 RPM. I want to operate elevator. Elevator should be run to 1 RPM. I need to run MRT system. MRT system, the car should be moved slowly until it reaches the door. Then the door can open. So I need to operate 1 RPM, not 30 RPM. Then people say there is no way, because if you use this technique, the minimum speed is 30. You cannot below 30. Why? Because the physical problem. So they have harmonics, and sometimes you have distortion. So your performance is between 1,800 RPM to 30 RPM. Then you say, I need 1 RPM. Then you have no opportunity because of the physical constraint, right? So people found, oh, this is not good enough. Then a student go to see his advisor. His advisor told him, oh, you have a good topic. Why don't you change to 1 RPM? So the student have to think. And then his response, I have no idea. Then the advisor said, then you cannot graduate, right? So finally, the student found some way. So we will check the next step. So people think this is not good enough. We have to improve it. So how can we improve it? Then people propose another idea, space vector. Space vector. So sinusoidal waveform has limitation. The limitation is 30 RPM. The idea is quite clear, but the performance is not good enough. So what does the student think? He say we have A phase, we call 100. We have B phase, maybe here. We put B phase here, 0, 1, 0. We have C phase. C phase could be, so here we have 1, 1, 0. So 0, 0, 1. So we have A phase, we have B phase, we have C phase. Then here we can get A plus C is equal to B. So this is 1, 0, 1, right? And this is opposite to C phase, this A plus B. So it is 1, 1, 0. And here we can get 0, 1, 1. This is B plus C. So how many active steps do we have? 6. Right? We have 6 active vector. How many zero vector do we have? 1, 1, 1. And 0, 0, 0. We have 2 zero vectors. So if you operate a motor, what do you need? We hope the motor can rotate smoothly. So what do I need? I need a circle, right? So my voltage or my current should be a circle. If you have a circle, then in A phase, you can see the waveform is like this. Because projection. So we have vector here, the vector rotate. So when the vector come here, we can get A phase is P. When the vector run here, we go this way. When the vector go to A phase, it becomes 0, right? Projection. Then it go here, become negative. It come here, become minus negative. If it come here, become 0 again. So what is the real voltage vector? Should be a circle, right? A circle. But if we use the 6th step, what is your vector? Your vector, right? Here, go here, here. Here, go here, here. Here, go here, here. Here, here, here. It is not a circle, right? So 6th step is not a circle. What is a circle? Should be like this, smooth. So how can I create a vector like this? So if I run here, I need a vector here. How can I create? If I need a vector here, how can I create? We can use math. We can think of, we learn projection. So it should be here. It should be here. It could be VA, but we have duty cycle for VA multiplied by 10 ohm T. So maybe we call this is T1. So VA is here. We have to multiply T1T. And we have here, this is minus VB. So minus VB. And what is the duty cycle? Only here. T2 divided by T, right? We can use synthesize. We call this. If you have A vector, if you have B vector, how can you create C vector? It is A plus B, right? A plus B is C. However, if I need half C vector, how can you get half C? You have projection here. You have projection here. So you can say, I have A vector, but I control the duty half. I have B vector, I control the duty half. So half A, half B become here, right? So we can create this vector. Then you ask, how can I create this vector? So you have to do projection to compute maybe 0.8A plus 0.2B. It become this vector. So I have to change my vector according to the time. So first I'm here, then I'm here, then I'm here, then I'm here. So I can compute online instantaneously. Then I can create duty cycle. Then I can drive my inverter. So the idea is quite simple. So the real vector depends on A phase plus B phase plus C phase. And then we use the math to compute how many for A phase, how many for B phase, how many for C phase, how many for zero vector. Then we can synthesize any vector here, 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 but we cannot over here. It is impossible, right? So we have to limit in the circle. So then we can synthesize by control the duty, and it will work. So the student proposed this idea, and finally he graduated because this is a new idea. It is quite good, and we can synthesize any vector. Why do we synthesize any vector? Because we should control a motor. A motor should be a circle for its vector, for its current, for its flux. So we need a circle. If we need a circle, we have to use synthesize. If I am here, then A and B synthesize. If I am here, then B and minus A. If I am here, then I use minus A and B. If I am here, then I could use A and minus C. So we have to understand which location, which region is our voltage vector. And then we use the mathematical to compute the duty cycle. And then we output the duty cycle to control the inverter. then we can create dynamic voltage vector. So the amplitude can be adjustable, the angle can be adjustable. But what is the disadvantage? You need a very good DSP because the vector is moving. Sometimes here, but here it becomes larger because you have transient. Then here it becomes smaller. So you have to compute every time. And if your DSP is too slow, then your vector move here, but you output here, then it fails. So your DSP should be as quick as possible. So what is your sampling time? It could be 100 microseconds to finish one vector. So what is your frequency? 10 kilohertz. So the frequency becomes 10 kilohertz. Why don't you push to 20 kilohertz? Because you haven't computed yet. You're not finished. If you're not finished, then you can control the vector. So you have to compute one time, then control one time, right? So it depends on your DSP computation ability. But you say, I'm sorry, my DSP is very busy. My DSP should be do the speed control. My DSP should be do the torque control. So he is very busy. It is very busy. So how can I put one DSP only for PWM? Then how many DSP do I need? I need one DSP for PWM, another DSP for speed. So I need two DSP, right? And they should to talk each other. So what is the problem? The problem is your DSP has a very heavy load. So if you need the DSP too much, then speed you do not have enough time to handle. So we have to consider the real situation. But finally, the idea is very successful, especially for motor drive. So now everybody use space vector because it is more accurate. The response is more quick and it is perfect. So if you need a vector, you have to compute. Use V1 and V2 to synthesize the vector. So you have to compute the duty cycle of V1 and the duty cycle of V2 and the duty cycle of the zero vector. Then you can output T1, T2 to drive this to drive V1, this to drive V2, this to drive zero vector. Then you can have the vector. So this is general idea. So finally, it is a very good step because people use this and it is very successful. And recently, people say, oh, this is not good. We need a better. So how can we get better than this one? So people ask one question. If you control the motor, do you need a current or do you need a voltage? So if you control a motor, what do you need? You need to control the speed, right? Motor speed or motor operation, right? So my motor is a robot. It is operation control. So if you control a speed or if you control a motor, what do you need to control? Torque, right? So speed comes from torque. So you can see torque equal to J omega dot. So you need to control what? Torque. Then you control the speed. Can you control the voltage to control the speed? To control the torque. So what is related to torque? Which one related to torque? So motor torque is related to voltage or current. If you want to control a robot, do you need to control current or do you need to control voltage? Current, not voltage, right? Because torque is equal to your excess current multiplied by torque constant. So if you drive a car, you control the gasoline, right? If you put more gasoline, then speed is become higher. If you control a motor, what do you need to control? Current. If you control the current, you can get positive torque, or high torque, or small torque. But if you control voltage, then what happens? The voltage go to the dynamic equation and create current, and then the current create torque. But here from voltage to current, it is related to resistance, related to inductance, and related to back EMF. It is very complicated. So I don't know how to control voltage. It is too complicated. So if you drive a car, you want to control the speed, do you control the panel direction? No. You only control your gasoline, right? So now, if you want to control a motor, what do you need to control? Current. So if you want to control a motor for current, why do you control voltage vector? It is not a link. So this is the reason your performance is not good. So you have to change your idea to say, if I want to control a torque, I need to control a current. Not I need to control a voltage vector. So it is indirect. So they say we have to measure the current, and we have designed the current to close the desired current. So what is our desired current? Fs. So this is our desire. So our current should be as close as possible. It could be like this. So then my torque is good. But I cannot control voltage, but I don't know what is my voltage. Right? So in this reason, they think you have better to control your current. How can you control your current? You can measure your current. So you just measure your current, and this is your desired current. Then you try to analyze the current position. So this is my desired current, right? And then now my current is here. So how many choices? I have V1, I have V2, I have V3, I have V4, I have V5, I have V6, I have V0, I have V7. 8 choice, right? We have 8 choice. So if I am here, my current is here, what is my next step? If I choose V1, then my current go here. Is it good? Maybe not good. If I choose V2, my current go here. It is good, right? Because this is desired. I close to my desire. If I choose V3, then go this way. Not good. V4, go this way. Not good. V5, go this way. Not good. V6, go this way. Not good. V7, go this way. Then I can know the best way is to choose V2. Because V2 can get close to my desire. So we call this is prediction. So I predict if I choose V2, then I can get this current. This current is what I need. So we call this is predictive control. So the idea is very simple. I just calculate each vector to see which one is the best of my choice. Then I choose it. I never made a mistake. So then we can get a perfect current. So we call this is prediction. So what is prediction? You can see if I graduate, I have to predict what is my life in 5 years. So what should I do? I need to buy a house or an apartment. Then I have to calculate how much money can I make every month. How much money should I spend every month? And which location do I want to buy my house? If I only consider 1 month, then I think, oh, only can buy small house far away because I have no money. But you didn't account. Maybe every 5 years, your money become twice, right? And then you get married, you need a larger house. If you buy this house, after 4 years, you have to sell the house and buy a new house. And then you lose more money. So this optimization is only current, not future. So if you want to do optimization, you have to consider your past, your present, and then your future. And then you put everything together, right? So you have to consider maybe 5 years, 10 years. If I buy this one, then I have to sell it. But if I buy another one, now I have to get a loan from bank. But I can pay for it by my salary. So after 10 years, I have a big house. And the location is good. So which is better? This is better. So what do you need? Predictive. So this control is predictive control. You have to consider next 3 steps or next 4 steps. And you have to choose the best one. And then you control it, you send out. But the problem is computation is quite complicated. So you need a good DSP. And another disadvantage is it rely on your parameter or your model. So you need inductance. If your inductance is wrong, then your current projection is wrong. So if you want to buy a house, you need a precise information, right? So you have to make sure you didn't get fired. You have to make sure the location in the future is good. You have to make sure you can handle it, then you do it, then you will be the winner. So the most important part is accuracy. So you have to get the parameters of the motor, accurate parameters of the motor. But can you get precise inductance of the motor? The answer is no. Because if you add the load, then the current increase. If the current increase, the inductance decrease. So the inductance is not always constant. It is rely on situation. And also your inductance, your resistance is rely on temperature. So when you run the motor, it only 30 degrees. But after 1 hour, become 100 degrees. So your resistance changed. And sometimes your load, your initial change. So the problem is you never get the precise parameters. So if you buy a house, you never get the precise information because one policy come here, then everything change. So you say, I still lose because I didn't calculate this part. So we need precise parameters. So we call this is predictive control. Now this algorithm become more and more important. The reason is DSP become more and more powerful. So we can have enough time to do the calculation as quick as possible. So now a lot of people investigate the predictive PWM modulation, and they can show if I use this, it is better than the vector control, the space vector. So it will become a new trend. So I think we can stop here and we can have 10 minutes break.